So far in this topic, we have been applying Fourier series analysis to periodic functions, functions that repeat themselves with some sort of regularity. In this lecture, we're going to use those ideas for functions that are not periodic, functions that are defined over some interval. Now that might sound contradictory. How do I apply Fourier analysis, which involves expressing my function in terms of sines and cosines, which repeat themselves forever? How do I apply that kind of analysis to a function which is only defined between 2 points? Well, the approach that we're going to take is to take our function over that finite interval and then make it a periodic function by repeating it again and again. And then we'll apply a Fourier series analysis that will also apply over our original interval. However, as we're going to see, we don't want to just make any old periodic function. As we've already seen in this topic that if a function has some sort of symmetry, like it's odd or even, then it's very straightforward to calculate the Fourier series. So instead of just periodically extending our function, we're going to look at the odd and even periodic extensions of our function and then calculate the Fourier series. So by the end of this lecture, you'll be able to calculate the Fourier series of any function defined over a finite interval. So we'll start by reminding ourselves, how do we create periodic functions from functions that are not periodic? So let's take a look at example 1. We've got a function here defined between 0 and 3, and it's given by the absolute value of x minus 1. So let's sketch our function over the interval 0 to 3, and then look at its periodic extension. So between 0 and 3, we've got f of x is equal to x minus 1. So you can see that it's going to be a positive number, and it's going to change at the value 1. So let's look at the interval 0 to 3. For positive values of x minus 1, this thing is going to do nothing, so it's just going to be the line from 0 to 2. And for negative values of x minus 1, that is for x between 0 and 1, this thing is going to make it positive. So you can almost imagine that I've taken this line and reflected it so that it's always positive. That's what the absolute value does, those vertical lines. Let's take a look at what happens at the discontinuities, or the edges of my domain. So I'm including this point and I'm excluding this point, and they connect right here. So this is my basic function f. Let's indicate that right here. Now, I want to create the periodic extension of f, so what I'm going to do is I'm going to copy and paste. Pick this thing up, move it over 3 units, and paste it again. I know I need to move it over 3 units because the basic width of this thing is 3. So let's sketch this between minus 9 and 9. So I'm going to use a different color here so I can tell the difference between the periodic extension and my original function. So you can see that the width of my original function was 3, so the period of my function is 3 as well. And there we go. So you can see that there's discontinuities at minus 6, minus 3, 0, and so on. So we're going to indicate this function by f periodic. I'm going to call it f periodic, just so I can distinguish it from my original function f of x. And of course, those two things are the same on the original interval. So what I mean by that is that f periodic of x is equal to f of x for the following values of x. for 0 is less than or equals to x is less than 3. So in other words, what I mean by this is that f of x is only defined between 0 and 3. F periodic of x is defined over the entire real line, and they match up between 0 and 3. The advantage of that is that when I do a Fourier series analysis, I'm not going to do the Fourier series analysis of f of x. I can't, because it's only defined between 0 and 3. But I can do a Fourier series analysis for f periodic, because that's a periodic function. And because f periodic and f of x match between 0 and 3, the Fourier series for f periodic will also match f of x between 0 and 3. Now, as you can see, there's no symmetry for this periodic function. If I flip it left-right or left-right up-down, I don't get the same function again. So I'm going to, instead of defining f periodic, I'm going to define the odd and even periodic extensions of f and sketch them as well. So let's take a look at those. Starting with the even periodic extension. Again, let's sketch our original function in blue. Here it is. So I'm not including that point, and I am including that point, and this is the value 2. Here's 3 and minus 3. So remember how to create the even periodic extension. I first of all take my basic tile, which is shown in blue here, and I double it in size by flipping it left-right. So I'm going to get something like this. So this is now my basic tile. I've got it twice as wide, so the period is going to be 6. That's compared with the period of 3 in the last example. So here we've got twice as large a tile, so the period is 6, and this is then the basic thing that I'll repeat. So including that point, not including those points, and something like that. So we're going to call this f even, by which we mean it's the even periodic extension of f. So again, let's indicate on our figure here what the original function was. Here it is in blue. And in purple, I've sketched the even periodic extension of that. So we're going to call that f even. Now we need to decide what happens at the edges of our basic tile. So let's take a look. I have a little bit of freedom in terms of choosing the value of f even x at the values x is equal to 3, x is equal to 9, x is equal to minus 3, and x is equal to minus 9. Because I have this open circle here lying on top of each other, I need to choose a value for that, and the most sensible thing to do is just to fill it in. Remember, it's not going to make a difference for my Fourier series because the Fourier series gets rid of discontinuities. It makes my function continuous. So there's a very small difference between my function f even and my function f of x, but it only occurs at the very edge of the tile that I'm repeating. So once again, we notice that f even and fx itself are the same over the original interval. So f even x is equal to f of x on the interval 0 is less than or equal to x is less than 3. So once again, I've taken my function f of x, I've created a periodic function that has even symmetry. It's f even. That now I can calculate its Fourier series because it's a periodic function. And that Fourier series is going to match f of x between 0 and 3 because f even matches f of x between 0 and 3. This is the case now for the even periodic extension. Let's take a look at the odd periodic extension. If you are feeling comfortable with this material now, you can pause the video and try and sketch what that would look like yourself. Go. All right. So we want to sketch the odd periodic extension. Once again, we're going to start off by sketching what it looks like between 0 and 3. Zero to 3. It's taking values 1 and 2. And once again, what we're going to do is we're going to create a tile that's twice as large by using odd symmetry. So I'm going to flip it left, right, and then I'm going to flip it upside down. So it might be useful just to sketch, first of all, what it looks like if I flip it left, right. So that would be the same as the even periodic extension. Let's do it in purple so we don't get confused. And I'm doing a dashed line here to indicate just that this is not actually what I'm going to do. And then I'm going to take that dashed purple line and flip it upside down. So I'm going to get something like this. Okay. So this is now my odd tile. So I've taken my original tile, f of x, and I've created an odd tile by flipping it left, right, and then upside down. Notice that we have to think a little bit more carefully about what happens right here at x is equal to 0, because I've got two different values for the same function, for the same value of x. Now that can't happen, of course, so I'm going to have to choose a value for x is equal to 0. And I'm going to choose the value 0, because that's the only value it can take for this thing to be truly odd. So I'm going to remove that closed circle there. Whoops. Won't let me. So that's okay. We'll put a black circle over it just to indicate that these are not included here and not included here. Okay. Okay, so that's our basic tile. You can see, just like in the even case, it's twice as large, so the period of my odd periodic extension is going to be twice as big. It's going to be 6. And this is the thing I'm going to repeat. So let's show what that looks like. So I'll get something like that. And then that. And over this side, I'll get something like that, and then that. So I'm not including that, I'm not including that. I'm not including this point, and I'm not including this point over here. Now notice that I also need to decide what happens at 9 and minus 9 and minus 3 and 3. You see, I don't have values for these functions here or here or here or here. So once again, I'm going to choose that to be 0, because that's the only value it can take for this to be really a truly odd function. And just to avoid any confusion, let's get rid of those dashed lines now. We don't need them. There we go. So here is my odd function. Use a different color for the period, again, so we don't get confused. There we go. So let's indicate our original function in here. This is f of x in blue. And in purple I've got what we call f odd. So this is the odd periodic extension. And once again, f odd and f even exactly match each other on the original interval. F odd and f of x, excuse me, exactly match each other on x between 0 and 3. So once again, I can use Fourier series analysis on f odd to find the Fourier components. The resulting Fourier series will be the same as f of x on the original interval because f odd is the same as f of x on my original interval. So one thing you notice here is that there's actually many different ways to create a periodic function from a non-periodic function, a function that's just defined over a particular interval. We've seen here the odd periodic extension, the even periodic extension, and just a periodic extension with no symmetry. And the resulting Fourier series will be slightly different. So in the case of the even periodic extension, we saw that we will, because it's an even function, we'll get a cosine, a Fourier cosine series. Because of the even symmetry. And for an odd periodic extension, we saw that we'll get a Fourier sine series. That is, a whole bunch of those Fourier coefficients will be equals to 0 when I calculate the Fourier series for the odd and even periodic extensions. Now in the case of just the periodic function, the original one we looked at, just the periodic extension, there's no symmetry, so we'll have both cosines and sines. All three of these cases are called half-range expansions. They're called half-range expansions because I'm taking my function f of x, and that's going to be half of my original tile, my basic tile, which I'll then make periodic. So I'm basically taking half of the range and extending it periodically. Now this allows us to define the Fourier series for functions over finite intervals. Let's take a look at another example. Again, we're going to look at the periodic extension, the odd periodic extension, and the even periodic extension of a function f of x defined between 0 and 1. So let's start off with the periodic extension. So this time we're going to define our function between 0 and 1. So let's say that's 1, 2, and 3. Minus 1, minus 2, minus 3. And our function is between 0 and 1. It's given by x squared plus 1. So that's going to be something that looks like this. So we're including this point and not including that point. And that's our basic function, f of x. So we're going to create the periodic extension of this just by copying and pasting it. Again, I'll use purple for that. And you can see that the period of this is going to be given by the period of the size of my original function, the interval over which it was defined. So it's just going to be a period of 1. Okay, so this is just the periodic extension, so we'll call this f periodic. and the period is the width of my original tile, so it's just equals to 1. So there is the periodic extension, and you can see if I took the Fourier series of that, I would end up with cosines and sines. So instead, let's look at the even periodic extension. So once again, let's sketch our function between 0 and 1. And then we're going to double the size of that by flipping it left-right, taking its mirror image. And then this is the basic tile that I'll repeat. So the width of that basic tile is twice as large, so the period of this function will be 2. So let's sketch what this looks like between -3 and 3. And you can see that I've got some open circles lying on top of each other. So again, I have a bit of freedom in terms of choosing what values this function takes at -3, -1, 1, and 3, where those tiles overlap. So I'm just going to make it equals to the value 2, which is this value here. So I'm going to call my original function f of x again. And my periodic extension is going to be f even, because it's the even periodic extension. And the period is equal to 2. Now let's take a look at the odd periodic extension. Here's my original function. I'm going to create the odd tile. Let's leave that circle off for the moment, because I'm going to have to deal with what happens at x is equal to 0. I'm going to make an odd function by flipping this thing left-right. So it would do something like that. And then flipping it upside down. So you can see I would end up with something that looks like this. So it's going between -2 and 2. Now I need to decide what happens at x is equal to 0, and you can see that I'm going to have to take that value to be equals to 0, because that's the only odd function, the only value that would give me an odd function. So this is my basic tile, and this is the thing that's going to repeat itself. You can see it's twice as large, so the period is 2. And then let's copy and paste that tile. So I'm going to get something that looks like this. Kind of similar to the example we saw before. Now you can see that I've got some open circles still left to deal with. And those are at the values 3, 1, -1, -3. And again, because this is an odd function, those values have to be 0. There's no other values they can take. And there's a slight difference now between f odd and f even, but only at the very edges, and so we won't worry about that, because of course the Fourier series analysis doesn't care. So there's our even and odd periodic extensions. The even periodic extension will involve only cosines and of course the a0 as well. And f odd will only involve sines, the bn's. So now let's use these ideas to actually calculate the Fourier series for a non-periodic function defined over a finite interval. That is, let's find the half-range expansion for a function over a finite interval. So in this example, we've got a function defined between 0 and 2, and a periodic extension of that function would look something like this. Now, we've already seen that this periodic function, when we just do a periodic extension like this, we don't end up with any nice symmetry. So what we're going to do instead is look at the odd periodic extension. So that's sketched here. You can see it's got odd symmetry. If I flip left, right, and up, down, I get the same function. So let's calculate the Fourier sine series for this odd function. This is the odd periodic extension, so we'll call this f odd. And because f odd is odd, surprise, surprise, it means that all of the a zeros and the a n's will be equals to 0 by symmetry. So that leaves me with just bn. So we need to identify what the period of this function is. So we can see that the original function was defined between 0 and 2. When I doubled it in size to create an odd function, I created a periodic function with size 4. So t is equal to 4, which means that L, the half period, is equal to 2. So let's put that into our formula for Bn. So we're going to have 1 over L, integral from minus L to L, of f odd x times sine n pi x over L dx. Again, we're going to make use of symmetry here. F odd is odd, and sine is odd. So we have an even function. So I can replace this integral from minus 2 to 2 with an integral of 2 times the integral from 0 to 2. And the nice thing about that is that now f odd between 0 and 2 is exactly f of x. So I've managed to express my Fourier coefficient entirely in terms of f of x, my original function. So this is because fx is equal to f odd on 0 is less than or equal to x is less than 2. So now I can use my formula for that. That was x over 2 plus 1, and carry out that integration. So I've got the 2's cancel, so I get integral from 0 to 2 of x over 2 plus 1 sine n pi x over 2. Let's split that up into 2 pieces. So I can take out the factor of a half, x sine n pi x over 2. And I've got left over the integral from 0 to 2 of sine n pi x over 2 dx. So let's split those into 2 pieces. I'll do the first integral, I'll call that 1, and the second one I'll call 2. So 1 is going to be carried out by integration by parts. So just to write that out again, we got a half integral from 0 to 2 of x sine n pi x over 2 dx. We're going to do integration by parts. We're going to use u is equal to x and dv is equal to sine n pi x over 2 dx. So that's going to give me a half u times v, so that's x times the integral of sine n pi x over 2, which is minus cosine n pi x over 2, all divided by n pi divided by 2. I'll tidy that up a little bit. Let's write it like this: n pi x divided by 2 divided by n pi divided by 2. There we go. And that's from 0 to 2. Minus a half the integral of v du. So that's minus cosine n pi x divided by 2 all over n pi x divided by 2 times du, and du is just dx. So this is u, v, and v du. That's just integration by parts. So let's tidy that up a little. We can take out the factor minus 1 over n pi divided by 2. Dividing by n pi over 2 is like multiplying by 2 over n pi. So I got minus 1 over 2, 2 over n pi, x cosine n pi x divided by 2, from 0 to 2. I've got a minus and a minus, which gives me plus. Again, I've got a half times 2 over n pi. And I've got the integral of cosine. So that's going to be sine n pi x divided by 2 all over n pi divided by 2, from 0 to 2. So let's put in values now. These factors of 2 will cancel out. These factors of 2 will cancel out. So I'm going to get minus 1 over n pi times, okay, so let's put x equals to 2 in here. I'm going to get 2 cosine n pi. Right, when x is equal to 2, the x and 2 cancel. Minus, what happens when x is equal to 0? Well, I've got 0 here, so that's going to give me 0. I've got 1 over n pi, and I've also got a factor of n pi over 2 on the bottom, so that'll become 2 over n squared pi squared. And I'm going to put in x is equal to 2 in here, so I've got sine n pi, and x is equal to 0. So these are going to be equal to 0. Sine of n pi is 0. And sine of 0 is 0. So that leaves me with just one term. Minus 2 over n pi. And remember that cosine n pi is equal to minus 1 to the power of n. So that's the first part. Let's look at the second integral I needed to carry out. This one is a little bit easier. So if the second part was equals to integral from 0 to 2 of sine n pi x over 2 dx. So if that's going to give me minus cosine n pi x divided by 2 all over n pi divided by 2 from 0 to 2. So that'll give me minus 2 over n pi cosine n pi plus 2 over n pi cosine of 0 So I'll get this is equal to minus 2 over n pi minus 1 to the power of n plus 2 over n pi times cosine of 0, which is 1. So let's put this together then. Bn is going to be 1 plus 2. So I get a minus 2 n pi minus 1 to the power of n and a minus 2 n pi minus 1 to the power of n. So that'll be minus 4 over n pi minus 1 to the power of n plus 2 over n pi. And notice that although, yes, I can look at the even and odd cases here, there's not going to be exact cancellation. So none of these are going to be equals to 0. They're all going to contribute. So let's take a look at the first couple of terms here. Here's my expansion. F of odd is equal to sum from n equals 1 to infinity of, here's my bn and sine n pi x over 2, because this is the Fourier sine series. I'm dealing with an odd function. Notice that I wrote here f odd of x rather than f of x, because f of x is only defined between 0 and 2. Whereas this is defined for all values of x. This is the odd periodic extension. Here's the first couple of terms, and you can write, I can actually sketch the graph of the first 20 terms here. So here it is, and you can see my original function is sort of definitely being sketched out here. Between 0 and 2, here's my original function. And then the periodic extension would have been something like this. So you can definitely see it's sort of starting to match up. But the problem, of course, is that I have this effect at the discontinuities. At the discontinuities, my Fourier series is trying to do two things. It's trying to make it a continuous function, so it's jumping from 2 to minus 2 and minus 1 to 1. Because of course it has to be a continuous function. And I'm also getting this ringing effect that always happens when I have discontinuities in functions and then take their Fourier series. This happens because the function suddenly changes value, and the Fourier series thinks that it can deal with that by just adding in higher and higher frequencies. So you can see here that the odd periodic extension resulted in a Fourier series that does match my original function from 0 to 2, but only when I add in enough Fourier terms. So what we're going to do next is do exactly the same problem, except this time look at the even periodic extension. So again, let's take a look at our original function. You can see it's defined here between 0 and 2. And then I've extended that, so it's periodic and it's even. So we'll call that f even. So let's calculate the Fourier series for this. So f even is an even function, which implies that all the bn's will be equals to 0 by symmetry. I can also figure out what a0 is because it's the average value of f of x. And because f of x, or f even of x, excuse me, and because f even of x is very simple here, I can just read off what the average value is. It's between minus 1 and 2, so the average value will be 3 over 2, or 1.5. If you have a more complicated function, you should certainly do the calculation. It's not that hard. Let's figure out what the period of this function is. You can see that I took my original function shown in blue here and doubled it in size to make an even function. So the period is going to be 4, which gives me a half period of 2. That's what I'm going to use now in my formula for the ANs. So I've just got one integral to do. 1 over L, integral from minus L to L of f even x cosine n pi x over 2 dx. Again, I'm going to make use of symmetry here. This is an even function, and this is an even function. Even by even is even. So I can replace this integral from minus 2 to 2 with an integral with twice the integral between 0 and 2. And again, the advantage of that is that now f of x is the same as f even of x. F of x and f even x are the same between 0 and 2. So I can use my original formula for f of x. So we know that that is equal to, the 2's cancel, so I get the integral from 0 to 2. F of x is x over 2 plus 1. Again, I'll split that into two integrals, so I get a half the integral from 0 to 2 of x cosine n pi x over 2. Plus the integral from 0 to 2 of cosine. And we'll call these 1 and 2. All right, so let's take a look at 1. We're going to have to do this by parts. So this is a half the integral from 0 to 2 of x cosine n pi x over 2 dx. So let's set u is equal to x, and cosine dx is dv. So integration by parts gives me u times v, the integral of cosine is sine, n pi x divided by 2 all over n pi divided by 2 from 0 to 2, minus a half the integral from 0 to 2 of v du. All right. Let's tidy up a little. You can see I can take this n pi over 2 outside, so it becomes 2 over n pi, leaving me with x sine n pi x divided by 2. Minus, again, I can take out the factor of n pi over 2 on the bottom. I've got the integral of sine, which is going to give me minus cosine n pi x divided by 2, all divided by n pi divided by 2, from 0 to 2. Sticking in the values of x, I've got one over n pi. X is equal to 2 sine n pi, minus, when x is equal to 0, that second term will vanish, so x equals to 0 substituted in here gives me 0. I can take out that minus 1 over n pi over 2. These 2's will cancel, and I'll be left with plus 2 over n squared pi squared cosine of n pi minus cosine of 0. So I know that sine of n pi is 0. I know that cosine of n pi is minus 1 to the n. And I know that this cosine 0 is equal to 1. So I've got this whole thing is equal to 2 over n squared pi squared minus 1 to the n minus 1. So you can see there's a danger here that some of my terms will vanish. For even n here, this will be equals to 0. But let's first of all carry out the integral for 2 first, before I try and look at the odd and even values of n. So 2 was equal to, remind ourselves, integral of cosine. So I can do that right away. We're going to get sine n pi x divided by 2 all over n pi divided by 2 from 0 to 2. So that's going to give me 2 over n pi sine n pi minus 2 over n pi sine of 0. So both of these are 0. So I get that second integral is equal to 0. So I finally have that an is equal to 2 over n squared pi squared minus 1 to the power of n minus 1. So as we saw, we need to look at separately the odd and even cases. So let's look at n is equal to 2k. It's equal to an even number. So k here is equal to 1, 2, 3, and so on. What are the corresponding coefficients? So we have a 2k. Everywhere I see n in that expression above, let's replace it with 2k. I've got minus 1 to the power of an odd number, of an even number is plus 1, minus 1. So all of the even a's are 0. So a2, a4, a6, a8 are all equals to 0. That leaves me with the odds. So k is equal to 0, 1, 2, and so on. So a 2k plus 1 is going to be equals to 2 over 2k plus 1 squared, pi squared, times minus 1 to an odd number, minus 1. So that'll give me minus 4 over 2k plus 1 squared, pi squared. So now my Fourier series becomes f odd here we go, f even, excuse me, is equal to, here's a0, I've got the sum from k equals to 0 to infinity, and here's all the odd a's. And this is the cosine series expansion for Fourier cosine series, because this is the even periodic extension of this function. So let's sketch what this function looks like. Here's the first 6 terms of that even cosine series. Again, you notice that I can see the original function quite easily. It's right here. So it matches quite nicely. And because there's no discontinuities in my even periodic extension, I don't have that issue that I had with the odd periodic extension, where this function had a lot of wobbles and frequent oscillations right near the edge of the discontinuity, and it also gave me a continuous function. Because the even periodic extension gives me a function that's already continuous, I don't have that issue, and in fact I get a pretty good approximation with just 6 terms compared to 20 terms in the last example. So the choice of even or odd periodic extension can often make a big difference in terms of how well the Fourier series is represented in the first couple of terms.